In this video, I'm going to talk about specific heat capacity. I'm going to talk about how to get its value from experimental data and also how to calculate it in problems. Please take a moment to read the success criteria I plan to cover during this video. So let's first start off with, what do we mean by specific heat capacity? Well, I have the definition here. So we have that the specific heat capacity is the thermal energy required to change the temperature of a substance by 1 Kelvin per unit mass. Let's think about the units that go along with that then. It's going to be the amount of thermal energy, so that's joules, per Kelvin per unit mass. Now here's the tricky thing about that. There are no standard units, so this could be joules per gram per Kelvin, like I wrote, or it could be kilojoules per kilogram per degree Celsius even. Okay, so in my statement here with 1 Kelvin, I could have written 1 Celsius. Each question you do, you need to double check the units they give for specific capacity so that you understand what units to use in your calculations. I also want to point out that this is the change in temperature, so there is no change in state or phase, whatever you want to call it. So if I'm talking about liquid, it's a liquid the whole time. If it's a solid, it's a solid the whole time. And a thing to note is that there's a different value of specific heat capacity for each one of those states. So how is that different from heat capacity? Well, specific heat capacity was the amount of energy per mass. So you need to realize that this is going to be for a specific material, whereas heat capacity so we've got the thermal energy needed to change the temperature of an object by 1 degree. It could be degree Kelvin or degree Celsius. That means its units are going to be joules, the amount of energy needed per Kelvin. Or, it could be joules, kilojoules again, but it also could be per Celsius. Specific heat capacity is going to be, for example, a value for water, whereas heat capacity would be the amount of energy needed to heat up the teacup that the water was in. So let's take an example here of how would I get to measure the specific heat capacity. Specific heat capacity. So here's one type of experiment that's fairly common. I have here, it says it's an iron cylinder. I've got a thermometer and an immersion heater. Immersion just means it goes inside. In this case, the metal. It could typically go in water as well. And you can see that I've got a power supply from my immersion heater, and I'll be able to calculate the amount of current going through it. And here's my voltmeter to measure the potential difference across it. Now, in this case, I had some values that I wrote down in an experiment I did. You can see the data here. Over time, every 2 minutes, I measured the temperature, and I've plotted my graph here. The data I have from my ammeter and voltmeter is the ammeter told me that the current was 2.51 amps, and my voltage across the immersion heater was 9 volts. So what does that allow me to do? It allows me to calculate the power that I put into the immersion heater. So power is current times voltage. And if I pick up my calculator, I'm going to get 22.59. I'm going to keep all the extra decimal places for now, and I'll round later. Now you can see here I've got time on the bottom I've got temperature on the side, and I have a steady increase. So in this case, my gradient is going to give me the change in temperature over the change in time. So how does this relate back to specific heat capacity? Well, we have this equation. Q, which is the amount of heat we're adding in, equals M, the mass of the iron cylinder in this case, C, the specific heat capacity we're looking for, times delta T, which is the temperature change. And because it's delta T, that's why we can do it in either Kelvin or Celsius. A change in 1 degree Kelvin is the same as 1 degree Celsius. Now, how am I going to be able to use my gradient, or this idea that we have power? If I divide both sides of my equation by T for time, well, energy per time, that is now my power. And this delta T over little t we have set as my gradient. I'm just going to write the word gradient for now. If I rearrange this, that means my specific heat capacity is going to be the power divided by the mass of the iron cylinder times by my gradient. In this case, my power, 22.59. The mass of my iron cylinder was actually 2,000 grams. I'll write that up here. And my gradient, which you probably can't see written there, but I'll give it to you. It is 0.02582. If I put that on my calculator, I'm getting the answer of 0.437 joules per gram per degree Celsius. And if I look online, the accepted value for this is 0.460. So it's actually not that bad. So here's another design that we sometimes use to measure the specific heat capacity. You can see I have a kettle here. And what I've done is I've put my thermometer inside my kettle, and I've now measured it every 30 seconds and wrote down the temperature. And you can see my line here goes up and starts to flatten off. Up here, the water's starting to boil. Now there may be some systematic error in my thermometer because you can see that it's starting to happen around 98.6. We're looking at getting things constant rather than the 100 degrees. But what we're going to be using is the rate of change of temperature again. So even if we had a systematic error and all these values are dropped a little bit, that's okay, because it won't change the gradient of this line. It's just shifting it up or down. If I start again with our equation for specific heat capacity, Q equals mc delta T. Again, I'm going to divide both sides by T for time. And on this side, notice my line of best fit is only using where the temperature is actually changing. It's avoiding this area that is where it's starting to boil. Now, my kettle, you can see here, it's usually written on the bottom, or you could go and find other ways to make this more exact, but my power on the bottom of my kettle said 2,200 watts. The mass in this case has to be the mass of the thing that's undergoing the temperature change, so that would be my volume of water, and I had 2 liters. That would be 2 kilograms for a mass. And again, we can rearrange this. Power, mass, C, and I'll write the word gradient so we don't get confused. C is going to be my power over the mass times the gradient, 2,200 over 2,000. And if you can read it up there, my gradient is 0.2647, giving me a value of 41556, and my mass was in grams, and my temperature was in Celsius. And that's pretty close to the real value of 4.186. So again, a pretty good experiment. So now that we know how we can calculate the specific heat capacity, let's do some more work with our equation. So in this case, we've got a mass of 200. It tells us the specific heat capacity, so that's C. Joules per kilogram degrees Celsius. So since this says kilogram, that means I need to put my mass into kilograms. It's a lot easier to do that, to change the simple mass, than it is to change the specific heat capacity. The change in temperature is going to be 110 minus 20, giving me 90. And let's put it in our equation. And since this is a multiple choice question, we should be able to do it without a calculator. So just a quick look. We've got 1, 2, 3 zeros. So this and this can't be true. I'm going to have 81 times 0.2. So 80 times 2, that's going to be 160. Take away one of the tens. So I'm going to get 16, and I had rounded that. Could have said 8.1, and then there's our zeros. The answer is C. Okay, so this is a question about a heat capacity. Remember, the heat capacity is the amount of joules per temperature that we need in order to raise the temperature by 1 degree. They're telling us that this letter is C. There's a mass, its mass is 2. So let's look at number 1. Increase the temperature of the whole object by change in T. In this case, it's a little confusing. It's talking about this T being temperature. C is the value to increase by 1 degree. So if I want to increase it, say 10 degrees, I'd have to multiply it by 10. That's actually the answer. Let's check down here and make sure that the rest of the values are not correct. The increase in temperature of per unit mass of the object. No, it's for the whole object already. There's only mass in our specific heat capacity equation. To melt the whole object? No. For both of these, heat capacity is about a temperature change, not a phase change, or not a change of state. The answer really is A. Example 3. The diagram shows a set of apparatus used to determine the specific heat capacity of water. This is like the first example I showed you. What does not affect the rate at which energy is lost to the surroundings? Well, let's just remind us, we can lose heat by conduction. That's through touch. We could lose it by convection. And that's through a fluid rising when less dense, sinking when more dense, and things with a higher temperature then have less density and rise. And finally, there's radiation. And most of the time when we talk about heat, radiation implies infrared radiation. So let's take a look. Insulating the container. Insulating the container. That would stop the liquid from transferring heat to the air right beside it. Now, if it's right beside it, we can talk about it being conduction. But then once the air is heated, it would be convection as it moves away. Depends on how we want to phrase that. Placing a lid on the container, well, that will stop convection. It will stop the warmer air at the top of the water leaving the system. Polishing the outside surface of the container. Well, that's about radiation. If it's more likely to reflect, then it's also more likely to emit. infrared radiation. The two are related. So this would actually have an effect. And moving the thermometer closer to the heater, that's the one that has no effect about how energy is lost to the surroundings. That means our answer is D. Example 4. We have 200 grams of a liquid with an electric heater, and it has a constant power output of 100 watts. After 120 seconds, the rise in temperature is 50 degrees, and we're asked to calculate the specific heat capacity. So let's start with our equation for specific heat capacity. Remember, power is energy over time, so I can rearrange that and have energy as power times time. This is a little different because I'm not going to be using the gradient. So I'm going to put power and time here, mass, specific heat, and change in temperature. Let me move this around. Specific heat capacity is going to be power and time, moving these other to the other side, divided by mass, divided by the change in temperature. So if I put in some numbers, I'm going to have 100 watts and 120 seconds all over 200 grams. Let's double check. I've got grams here, but I have kilograms here. So I need to change that into decimal 2. And times the change in temperature, which will be 50. Now remember, in a multiple choice question, we should be able to do this without a calculator. That's why the values here are not calculated, but rather they're looking to see whether or not what you have here matches on this side. And in this case, you can see that the answer is A. We have a dishwasher with water starting at 16 degrees Celsius, and it's going to go up to 50 degrees before we're going to wash the dishes. Show that the energy must be supplied to the water to bring it to the correct temperature is 3 times 10 to the power 6 joules. I've got a few more pieces of information here. My mass of water is 18 kilograms. Specific heat capacity, oops, you can see I have some mistake here in terms of the units. I'm missing my minus ones. So let's calculate this. My equation, Q equals mc delta T. And we are looking for the heat, the amount of energy added in. So my mass in kilograms, let's double check that these match. Yes, they're both in kilograms, so this will be 18 times the specific heat capacity, 4,200 joules, kilograms, and it says Kelvin, but remember the change in 1 degree Kelvin is the same as the change in 1 degree Celsius. So in our case, it's going to be 50 minus 16. We need the change in temperature. If I pick up my calculator, 2, 5, 7, and 4 zeros. Remember, when we're doing these, show that question. You have to show your work. Show the equation with the numbers substituted in and the unrounded answer. Don't just go right to the end. Now, if I round this, I'm going to have 3, and then 1, 2, 3, 4, 5, 6. Times 10 to the power 6. That is what we're looking for. And I'm going to do an approximately value here to show that I'm rounding and the correct units. I've put Celsius, but remember Celsius or Kelvin, it doesn't matter. Part B. The power of the heater of the dishwasher is 1,800 watts. Calculate the time it will take for the water to be brought to the correct temperature. So, our equation for power is energy over time. If I move this around for time, that'll be energy over power. We just calculated the value of the energy. I'm going to use my unrounded answer. This would be one of those times where even if you did A and you got the wrong answer, you will be expected to either use your unrounded answer, which rounded correctly, or if you couldn't get A, you must use this value here in B. If I pick up my calculator now, I'm going to get 1,428 seconds. If I round that to two significant figures, because that's all this one has, that's 1.4 times 10 to the power 3 seconds. And finally, C. State the assumption necessary to perform that calculation. Well, I assumed that this energy here, the amount of energy needed to raise this mass by this change in temperature, was what we used. I assumed all of the heat or thermal energy from the dishwasher went to the water and nowhere else. So, what does that mean? It means in reality, I will need a larger amount of time because I will need more heat than this. In reality, some of the heat actually will go to the dishwasher itself or the surroundings around it. If you've ever touched a dishwasher front and felt that it was warm, that means heat was allowed to escape. And this is very important for any experiment in terms of calculating heat or specific heat capacity. Almost always we have heat loss, and what you need to be able to do is go back and look to say, what effect would this have on my values? Would I need more heat? Yes. So that means this number would actually be bigger and I would need more time. You can also do this in these questions is if I actually measured my heat from my experiment, Q is probably going to be larger than I really needed. And if Q was larger, then it would usually give me a larger than expected specific heat capacity. Please go back and read the success criteria. I hope you can say yes to all of these things after watching the video.